If we start with discussion, yeah, nobody will see. After the discussion, we can stop it, and that nobody really is affected in that. Okay, Detlef, it's your turn right now.
Yeah, thank you very much, Tobias. Well, I will not tell not only about the advantages, but I want also to talk a little bit about the disadvantages of
sorry, so I forgot something. If you have some questions, we should do it afterwards. Just write it in the chat, yeah, and I try to sort it. Please feel free in the chat to if you have some questions that we don't forgot them. Okay, thank you. See you.
Yeah. Okay. Or yeah, what I want to tell you about is not only about the instruments, but also about disadvantages and threats that comes up from the organism that we want to analyze. And the title is here from top to bottom. That means that we want to show you something about the investigations of water. And my topics here, I have just had a list, is talk a little bit about phytoplankton, what it is, and how this is related, for example, to the water quality. And with water quality, I mean that not only the different parameters that we usually measure, it is especially for the measurement of chlorophyll, which is a main feature of phytoplankton. I will tell you something about surface measurements and profiling. You saw in the beginning in the slide there I had the AlgaeTorch and the FluoroProbe I wanted to present today. Then we have some applications or case examples where I can show you how these measurements were performed. These instruments are now in use worldwide for different purposes, but I will tell you something which may fit also to your applications. And then at the end, I will tell you about some specific requirements which we think is important to use advanced fluorometry in analysis of algae and phytoplankton. So let's go to the first slide. This is a picture of some organism that we want to investigate and which you see from time to time. For example, here on the right side, it is a lake, a small lake in Kiel in very early spring, and the green color shows you that still under these conditions where it is cold and a little bit freezy, you see the development of the algae inside of this phytoplankton. That is algae, very small algae sometimes, and mostly are diatoms. In this case, for example, we have green algae, we have golden algae, and we have dinoflagellates and some other types taxonomically can be differentiated. And we have another group which does not really belong to the algae, the cyanobacteria, but they have similar features so that we can focus on them. This is an important group or class of phytoplankton which becomes more and more important in the past. So what I want to show you where you can find this phytoplankton, and here on the left side you can see it is also in winter time. It's a bloom in a small lake in a city of Hamburg, where you can see that it is flourishing, although the conditions are not very well. And what you see then that these are located at the surface, and of course, sorry, these organisms, they like to be very close to the surface because they need light to perform the photosynthesis. So this is an essential feature that they get the light. And when we look into a natural lake, for example, then we see different layers. We have here, for example, the epilimnion. So that is the classical expression for that, where you find probably most of them. Then we have a second zone, which is called the thermocline, where we find a jump in the temperature, and we have also the hypolimnion, which is the deepest layer here, what you can see here in this lower part. And in this different layers, you find probably all of the phytoplankton that is distributed in a water body. Why they are here, that is depends, of course, of a balance, and the balance is that what the organism needs. On one side, they need light, but on the other side, they avoid too strong UV light that comes from the sun. On the other side, they need, for example, nutrients like phosphorus or nitrogen. And the distribution is also subjected, of course, by the hydrodynamics of the water body. So, for example, if we have a flow or we have a mixing during summer, winter time, this affects also the distribution. And last not least, we have the grazers inside of this. This can be zooplankton, can be fish, for example, that also express their distribution, or they have an effect on the distribution of this phytoplankton. Well, the phytoplankton has advantages. For example, for us, they evolve oxygen, and they provide biomass, and they capture carbon dioxide, but they have also some disadvantage, and that is what I want to show here. And because this becomes more and more important, when the amount of phytoplankton is high, this will reduce, for example, the water quality, especially for those who need clear water. But this also can produce, these organisms can produce a big bloom of biomass, which is also called harmful algae blooms, because such harmful algae blooms, they often produce so-called biotoxins, especially the class of the cyanobacteria, the blue-green algae. They make special toxins, as you can see here in the bottom. That is the microcystin, which affects, for example, human health. Another disadvantage is this removal of algae and cyanobacteria. This raises costs, of course. This is a question of economics. And the last one, also in the same way, it is well known that from time to time you have fish kills all over the world, also in open seas, and provides economical damages with very high costs. So that is a quite good reason to look for the water quality and for the existence or abundance of this organism. And what we have here is that, of course, it is important to rate the water quality, let's say in a lake or in a reservoir. Here on the bottom, you see a picture from Poland, which I took 20 years ago in a reservoir close to a small town. This reservoir provides the water plant with with raw water for production of drinking water. And what you see here is there is a high amount of cyanobacteria which are mechanically stressed. And while this happens, the toxins can be released from the algae cells. So this is important, especially for the drinking water supply. So what we know is, of course, that there are other parameters like pH, pesticides, herbicides, turbidity, and nutrients, of course, bacteria, of course, and last not least, but also microalgae and cyanobacteria. And that is what we like to focus. It is not only essential for drinking water supply, because they have to remove it. It's also important, for example, for environmental monitoring. We have the Water Framework Directive, which clearly says to monitor this. We see this also, this rating, when you perform restoration. Restoration means treatment of spilled or polluted water. And during the last years, we have also some recommendations to survey bathing waters, because when people go inside of such a water, the toxins produced by cyanobacteria and other microalgae can affect the human health. Well, what we see is there are not that clear thresholds, levels, or guidelines, but it has to be shown that the number of algae cells, or for example, also the content of chlorophyll, which is a common molecule inside of all of these organisms, can be used as a level for production of drinking water, also for bathing water. What is allowed, what is recommended, it's not very clear, but these numbers are given by the World Health Organization, and you can see here on the right side where we have some levels of microgram chlorophyll A inside of the water, of bathing water or drinking water. So some recommendations exist, they are not very clear, but it is, let's say, a thumb value that you can use, for example, when you check water for the quality. So there is something which you can use, for example, when you use instruments for determination of the microalgae content. How this can be done, for example, this performance of phytoplankton rating. The first thing what usually is done, but it's not very practical when it is rather high, is the visual inspection. We have this, for example, in US America, we have a lot of volunteers, even pupils have to learn to view, make a picture with their smartphone and send it to the EPA to provide this information. It's rather late, it's not very sensitive. Other classic way is the sampling, and take the sample from the water, filtrate it, bring it to the microscope in the laboratory and count it. Also a little bit difficult and laborious, because it needs time and skilled people. So therefore it is a little bit difficult to perform this for a lot of samples. The other one, which is quite famous and probably also used mostly, also in the Netherlands, I know this, that you have a special way to make this, is a sampling and pigment extraction with organic solvent, and afterwards make photometry. I have it here. This is, for example, in international standard ISO, where the water quality is measured with biochemical parameters. We have here the spectrophotometric determination of chlorophyll A. Alternatively, I suggest here also to take into account the in vivo fluorometry, which is used in all our bbe fluorometers, which has some, I think, good advantage over the other methods. And we think it can be used alternatively to these classical methods. Some features of algae which makes it difficult to use the traditional methods is, for example, here on the left side, you see the Nanochloropsis. It is a very, very small algae. You cannot see this with a microscope because it's far too small. The other one here on the right side, it is a harmful algae, a blue-green algae, the microcystis, which produces also toxin. This forms, for example, colonies. So very, very difficult to count, to get an overview how much it is inside. So therefore, I think we have some better way to measure it with a fluorometrical device, which I show here. This is on the right side is the AlgaeTorch. This picture, what is shown here on the left, is a cyanobacteria, which can detect clearly. We focus here on chlorophyll from total microalgae and from cyanobacteria, so that we can catch this important group which forms the biotoxins. How this is measured, I can tell you very shortly here. This is a picture of the AlgaeTorch from the front, and you see here above the light sources. We have different LEDs which emit light, and this light is collected here by pigments of the algae cell, and it is transferred to the chlorophyll A. And a part of this chlorophyll A make fluorescent light. We can measure with the chlorophyll fluorescence detector, which is here located in the center of the head of the AlgaeTorch. And usually the algae use light to make photosynthesis, but when you have a very low amount of light and it is pulsed, as we perform this with the AlgaeTorch, then you can see that it cannot use this light for the reproduction, for the use of energy. You see only a very small amount of fluorometry. And in this case, you can see that the intensity of the fluorescence is correlated to the chlorophyll A content of the cell. So chlorophyll A content is a useful parameter to determine the algae content inside of the water. But why do we need now different wavelengths? You saw this in the picture that we have for the AlgaeTorch. We have 3 different LEDs. Algae, microalgae, and also cyanobacteria, they have very different pigments. And these pigments, they act as a trap, a light trap. And so that we have the situation that we need different light sources to excite all these peripheral antennae to transfer the energy to the chlorophyll A, where we can measure this fluorescence. So therefore, it is much more effective to use light sources which are adapted to the different photosystems inside of the algae cell. A simple blue light, which is used in most simple fluorometers, will not work efficiently, so that you will oversee a lot of algae when you have only one light source. That is the reason why we use different light sources in all of our instruments. This makes it also possible to make a quantitative measurement of the algae content and the cyanobacteria. What you see here is a typical situation, especially important also for pet owners. Well, we have here a situation where toxins are produced, which are also very harmful for, let's say, for pets, for dogs, cats, and so on. And we know a lot about of these accidents happened in the past, and still today, every day you can hear about this, that these animals are adapted. It's also the same for cattle and for horses. They should avoid to drink this type of water. I have also another message here on my desk. I want to show you, I want to tell you. For example, we had some spills or pollutions during the past years. Lake Erie, for example, is one of the biggest freshwater lakes located between US and Canada. And they have, due to a bloom, they have expanded lake, bottom dead zones, reduced fish population, foul beaches, and damages of local tourism industry, which generated more than 10 billion of revenue annually. So this is also what you can see, reason why it is important to monitor such upcoming blooms in an early event. And same place, city of Toledo, they had also a spill into the water, waterworks, fresh water for tap water, where some toxins came inside, and 500,000 people were affected. They have to switch to bottled water. So this is very important to know what happens inside of the water. And now I want to tell you something about the reason why we can do this with the AlgaeTorch. This is one thing that we see. We have the accessibility of this parameter that is very easy to access. That means we have it inside the water. We can easily measure it and it has a very high sensitivity. This, let's say, by the factor 10 to 100 more sensitive than the photometrical approach. Another reason to do this is, for example, we do not need any sample preparation. Just you can dip it inside, start the instrument, and measure it. So no laboratory work is needed to make this. As you can see here, my colleague Frederica is doing this from the Pioneer boat, where she measured immediately and get this in real time, because it is calculated very fast. Fluorometry is a very fast process, so that you can use it immediately at the place where you perform the measurement. And an advantage is also that this instrument is calibrated with the real algae. I can show you at the end of my presentation. And the values that you get from these measurements, they can be used as a proxy for other scale bases like biomass or other values that are interesting for the investigators. The handling is very easy. What you can see here is a part of the AlgaeTorch. You have soft key touches where you just have to touch it and you start the measurement. It's very simple. I can explain the use of such instrument in less than 10 minutes. For example, for bathing water surveyors, it is important to learn this immediately. It's not a scientific instrument with a lot of adjustments. And what you get out of here, it is, I think it's convincing. What you see is the content of cyanobacterial chlorophyll A. You see this here on this small screen. And you see the total chlorophyll A, which is the all chlorophyll microalgae cyanobacteria. So to get all of this. And in the background, I show you a map of Google Earth, where you can see we have an app where you can locate the different amounts, because this instrument uses GPS. You have not only the location, but you have also the amount of cyanobacteria and total chlorophyll A at different places. So this can be easily used also for publications, or use it for your reports when it is needed. So the value of this AlgaeTorch reading is that it can be used as a proxy for the phytoplankton abundance in real time. And it gives you the information that is needed for understanding what is the quality of the water. And the last thing, which is really important for many people of us, when we see that upcoming cyanobacteria is growing all over the world, you see if there is a threat of cyanobacterial toxins. Clearly to say, not all of the cyanobacteria produce these biotoxins, but many of them do then. So therefore it is, let's say, the AlgaeTorch can work as an early warning system to inform you about upcoming algae blooms and the potential risk of the water, even in an early stage. And what you can also see, of course, are the dynamics of the algae growth and the grow down after a bloom. Here I have now some examples. This was, sorry, I have to brush up my voice. From Brazil. We have visited a water plant and we performed some measurements, and I can show you something what we have done together with them. We performed depth profiles with the AlgaeTorch, and you see here on the different places, and we have here on the left side, on the upper part, the total chlorophyll and the blue-green algae, and you can see that we performed some measurements to the depths. This is not a very dense number of values, because the AlgaeTorch needs some time. You can submerge the AlgaeTorch to a certain place, and then you have to wait a few seconds. One measurement takes about 15 seconds, And then you can lower the instrument to another depth and take these measurements. And we have here going down to, let's say, to the depth of 5 meters. But what you can see is if you do not perform this measurement in that way, you will oversee a lot of algae which are in a certain depth. We have another AlgaeTorch which can go down to 100 meter. That is more important to cover the photozone. And with this instrument, we have also a depth meter where we can see where we are in the depths, and we cannot use it in this way where we had only a rope with this. But when we compare these results we obtained from the AlgaeTorch to another fluorometric device from bbe, that is a lab analyzer, and compare this to photometric approach. Here in this case, it's not ISO, it's acetone extraction. We see that the values are quite fairly good, so that we can say that the results obtained from the different instruments are quite similar. On the left side, you see the profiling again with this AlgaeTorch. And it is a little bit difficult to perform a full profile. So therefore, we use another instrument as shown here on the right side. It is the FluoroProbe. And the FluoroProbe is an instrument designed for profiling of a water body with a very dense measurement of values. This is a sketch of the instrument itself. You see here, this is the essential part. We have here the LEDs. Sorry, to go here. Yeah, we have the different LEDs where we emit the light. Here in the center of the window, we have the algae cells, and they emit the fluorescence. And then this is measured, or the signals are taken up for the photomultiplier and calculated with a microcontroller here above, which may be linked to a PC. On the other side, we have here the pressure sensor, which tells you something about the depth where we are inside of the water. So this instrument can perform rapid measurements. That means that we have, let's say, about 3 measurements per second. So that 10-meter profile can be done within, let's say, around about 30 seconds. So that means a very fast instrument and used in, well, let's say, more than 500 instruments are used all over the world. And I think this is also a good instrument, or maybe the best instrument available to perform these measurements. Not only get the information about the algae content in total, but also get the information about different algae classes. Because here we can not only get the information about cyanobacteria, but we can differentiate between different algae classes up to 5. Here, for example, I show you an example which was performed within a FluoroProbe in south of Germany, a CPAX here in October. Toby was there. And I just made a, except from this, what you see here in the depths, a profile where you can see that the cyanobacteria are prominent in a certain depth. And this allows you to quantify these cyanobacteria. If you perform this measurement only at the surface, which is mostly done by the authorizations, you will oversee this high amount of harmful algae. What you also can see that we have here yellow substances measurement. That is a decaying organic material which interferes with some signals. So there we have a correction for the measurements. Additionally, here we have made a measurement also of temperature and oxygen. We now provide a new combination of measurement of fluorometric oxygen measurement together with this FluoroProbe by an extra sensor which can combine with the FluoroProbe. So this is a new type of application where we can form algae measurements together with oxygen measurements, and we have temperature and depth. So here I have now a demo of software. I have to go outside of it a little bit. Now I see that I can make it. I need this one. Share. I hope you can see this. Can you see this, Toby? So this is a demo software that we have should simulate some of the way how we perform the measurement.
We can't see it. I think you have to move this demo to the other screen.
To the screen, I'm sharing. How does it work?
You have to share it to the head screen, Detlef.
Yeah.
It's the same screen as you have the presentation in PowerPoint.
Yes, you have to move the bbe++ from the one screen to the second screen.
How to make it?
Just move it from the top. You reduce the bbe++ software and move it to the other screen.
So this one. It's a mistake. Does not work. Okay, I will go over this. So I go back to this one. WebEx meeting. How to come back? Can you see the presentation again?
No, you have. I don't know why, but maybe.
Now?
Yeah, now we see it. Now we see it.
Yeah. Okay, then I will tell you. Doesn't matter. With the bbe FluoroProbe, we have a software developed especially for this, and there we installed a demo where we simulate profiling, and you can use this even if you do not have a FluoroProbe. You can download this and select profiling simulation in a demo mode, and then you can see how it works, how this is developing. I want to show this to you, but for some reason it's not possible to do this at this moment. Please ask us. We can show you where you can download it. Is from our website, and you can play a little around and to see how the features are. You can simulate everything. Just start with the point where you have the level of the height, for example, the pressure settings for the surface of the water, and then you can see how this profile is developing. Sorry for that, but I would like to continue. Then another case example. This is case in North Rhine-Westphalia, not very far away from the Netherlands, in Solingen, where we have the waterworks Glüder. And you see here the dam of the reservoir where they extract water, raw water, for the making drinking water from it. And this is what is subjected from time to time to growth of algae and also these cyanobacteria planktotics. And they use, for example, different instruments for the measurement of algae contents. They extract the water from different heights of this reservoir, where they have tubes with openings so that they can extract the water, but they perform also measurement of this water intake because they want to avoid the uptake of cyanobacteria and other algae inside of this water. So therefore they use different instruments. Here on the right side, of course, is the FluoroProbe. And this is a measurement of the reservoir. You see also here on the left side, this wall with the two towers for the extraction. And we did a travel or a trip over this lake and performed the measurement here at different places. And we especially looked for the occurrence of the planktotic rubescens, cyanobacteria, which is very well known to produce high amounts of biotoxins. That is a picture of the planktotic rubescens, and what we see here is only an example of one of the measuring places where we saw a deep layer of cyanobacteria at the depth of 12.5 meters. So what is important for them is to investigate and to follow up the dynamics of these growth of cyanobacteria inside of the water body, so that they can take measurements plans to avoid these, or start with counter measurements against the growth of these algae. Yeah, what else is important? Of course, I would like to tell you something about the turbidity measurement. This is also included in the AlgaeTorch, where it is important to make corrections. When you have turbid materials that swallows light, and this light is not possible to excite the pigments of the microalgae and cyanobacteria, and therefore we need to make some correction. Almost all of the fluorometers that exist on the market do not have this feature of the correction, although they have the measurement of the turbidity itself. So this has to be done handmade afterwards. Otherwise, you will find, let's say, wrong values with this instrument when the turbidity is increasing. We calibrate this with formacine, which is a standard for turbidity measurement. So you have this expression also in the screen of the AlgaeTorch. The same we have also, of course, for the FluoroProbe, where this is used as transmission measurement. Here I have reflection, but anyway, it's always important to have such kind of turbidity correction. Another thing which I meant in the beginning is, of course, the calibration important point. Many manufacturers, they use dyes for the calibration of their fluorometers. We think a better way is to use real algae, and we have it. We use real algae from our laboratory, where we keep them in a logarithmic growth phase, where we have also always high vital algae that are used for the calibration. And we think this is the best way to make a quantitative analysis when these instruments are calibrated with real algae from our cultures. We have 4 of them that we use classically for our instruments that stand for all the other algae. And what we know is that we sample natural algae which we find in the nature. So at the end, I think I show you a very old picture, but I write it because it comes from the Netherlands, which is a WML. Years ago, I don't think that this is still active, but you can see that they used it to survey also the quality of water that was used from the Meuse River pumped into a reservoir. They used a flow-through instrument shown here on the right side. We call it the Algae Online Analyzer, because online it means that it measures the algae content and cyanobacteria 24 hours, 7 days. And when algae came up, we have a threshold installed for this. This can trigger an alarm, which stop pumps and signal to a control room and start a sampler. Well, I use this because it was from the Netherlands, but it is used in other places worldwide, where we see that online measuring is a good way to monitor the content of algae. So at the end, you can see all the winter time is gone. We have now in the season But when you have a FluoroProbe, you're in a good situation. You can use it also in winter times or in autumn, wherever you are here in the Antarctica. And I can only tell you, thank you very much for your attention. I hope you got some information from this presentation. Thank you very much. And if you like, you may ask some question. Thank you very much.
Thank you, Detlef, for this presentation. Yes, I want to add a little topic that you really, what's also a benefit of the FluoroProbe of the big instrument, that we really measure the yellow substances, because the yellow substances has a big overlay in the fluorescence where also algae have a fluorescence. And if you don't make this estimation of the yellow substances, you have to be have an overestimation of algae. Just as a short feedback. Has someone a question? Please unmute your. We are not that much. Unmute your microphone and please ask them. I can start with that. That's one question. What is the minimum resolution of these instruments?
That depends on the way where you perform these measurements. Clearly to say, in the laboratory, you can say that we have for the FluoroProbe 0.05 microgram chlorophyll A per liter. Yeah? The minimum detection limit, as we did it in our laboratory, is under ideal condition, was 0.017 microgram per liter. It's a very small amount. But this is ideal condition in the laboratory. I think when we are at, let's say, at 0.1 microgram per liter under natural condition, it works quite well. The FluoroProbe has a photomultiplier inside, which makes this instrument very sensitive. The AlgaeTorch has photodiode as a sensor, which is not that sensitive, but you can say that we will have a resolution of, let's say, 0.1 microgram per liter. Maybe sometimes it is 0.15. It depends also, of course, on the offset, on the blank. When you want to measure very sensitive, you have to perform a blank measurement before you do this analysis. But I think under conditions where we measure, the sensitivity is high enough to work under most circumstances without any blank or offset measurements again. Is that okay for you?
Yes, please, someone else, some questions?
I cannot hear.
Has someone else some questions?
Yeah, I got another question. You talked about the FTU
Sure.
to measure the distribution.
Yeah, sorry, I did not get to the beginning of your question.
Okay, I will repeat it. I've also put it in the chat box, but I will repeat it. You have spoken about the turbidity.
Yeah.
And that is in the FTU unit. Is it equal to the NTU, the FTU?
Sorry?
Are the FTU and NTU equal to each other, or is there a big difference between it?
No, that is not the same. You can use it, but it's really not the same. We call it FTU because we use the formacine. Yeah, it depends on the angel, because we have the black scattering. The NTU usually is measured at a 90-degree angle. Yeah, and here we have a small angle because we have the backscattering, so that it is not easy to transform it. And I think maybe it's impossible to do this. But as we did this with the formacine, and we know the amount of formacine that we use for the calibration, we call it, of course, FTU. So therefore, it is not aimed, or it's not the goal of this measurement to get the information about the real turbidity. It is important what Tobias already mentioned. We use this for the correction, because the turbidity, as the yellow substance, they have an effect on the algae measurements, and therefore it is much more important to get this information, how much it has to be corrected, than to know about the real amount of turbid particles. Yeah, and one other thing which I have to mention, formazine is the standard, of course, but real turbid materials is not really comparable to the turbid particles which we have. They have other optical features. Yeah, for example, clay. Yeah, it has other sizes. It has the formazine. It looks a little bit like milk. Yeah, it's white and it's really dramatical reflecting. When we are in a water body where we have particles, they are sometimes colored. Yeah, so they have other optical features, and they stray the light in another way than, for example, the formazine. But we know that formazine is very well accepted all over the world, and so therefore we use it, and it is okay because we only use it for the correction. So if you want to really to rely on the values that you obtain and want to make a measurement of turbidity, I think a turbidometer is the better instrument to make it.
Okay.